the assignments in this control flow graph describe the SSA graph, and from a statement to its operands there is an edge. That means we have this graph. If we look at x, for instance, it's incremented here, and there is a phi function for x. It starts, well, that's not shown in the source code, but we assume it starts with 0, and then it's incremented in the loop. Okay, so this part of the SSA graph concerns x. Then x is incremented with t2, which gets its value from the memory read, which uses I1 as an operand to, I mean it uses t1, but the t1 is defined by I1 times 8, and I is of course the induction variable, and it's defined by this strongly connected component. The zeros, they are their own strongly connected components, as well as this one. So what we want to do is to find the strongly connected components, and not only that, we want to process them from the innermost to the outermost strongly connected component. That means, well, it means that it's important to have processed this strongly connected component before we see this one, or process it. And actually we can start with any node and just call strong connect. So we will do that and see what we can do with this. Well, in green, they are the processed vertices in strongly connected component, and the soon to be red ones, they are on the stack. Okay, so we finish that, and then the stack is empty, and there is not much to do with that one, so we continue with the next one, and it will it will discover this, and the search will continue to the other nodes. So these are on the stack, and then we continue here, and that one's also on the stack, and we continue there, and now we come to this, which will continue up to I0, and since that's a strongly connected component by itself, it's popped from the stack, and then we will notice that this is a strongly connected component, and then when we have identified a strongly connected component, we classify it to see if it's useful for the optimization. So this strongly connected component is not very useful, but this one is. And what we do is to check the format of this strongly connected component. There may be multiple assignments to the variable, so it's not necessary that it's only two nodes and only one increment, but there needs to be a phi function. Okay, so when we have processed this, we conclude that it's an induction variable, and the I is incremented with a region constant. In this case, it's constant. I mean, it's a number, but it could have been something else which is not modified in this region. Okay, so what we need to do is to find, well, first of all, due to the structure of this strongly connected component, it must be in a loop, and there must be a loop header which we identify, and if we have a variable which is defined in a vertex which strictly dominates the loop header and therefore everything in the loop, then that's a region constant. Okay, so what should we do here? When we have this multiplication, what we want to do is to change it from a multiplication to add. And now comes the nice thing with this algorithm. We simply copy the structure of this strongly connected component and modify this constant with the factor that we multiply the strongly connected component with. So we can create a new strongly connected component like this, like this, and define, we put a new variable here and forget about T1, and this Y1 uses this strongly connected component instead. So how should we copy it? Well, we traverse the strongly connected component backwards recursively and copy nodes along as we go. Then what happens is that this old strongly connected component, it will no longer be used. So what we should do is to remove it. But we will actually not do that. We will just let it be there, and then we will use the algorithm, dead code elimination, to remove such instructions.